Okay, this is the second and hopefully last lecture for this chapter. We're going to try to just knock this thing out. Covered a lot of ground today. We left off with the making snow. Now we're going to talk about enthalpy, which is something you've worked a little bit with already in class, hopefully. Yesterday we talked a little bit about this. I believe delta E is equal to Q heat plus W work. We talked about their units of joules and kilojoules. At constant pressure here we can see that our delta E is related to our delta H, our enthalpy, minus our pressure delta V. And so then you can rearrange that to say the enthalpy, which is basically heat given off, is equal to energy plus the P delta V. So there are a lot of variables we can include in these equations. Enthalpy, like I said, we can kind of think of it as heat. It's a value used to quantify heat flow into or out of a system in a process that occurs at a constant pressure. So you'll see negative delta H, positive delta H. If it's negative, you're talking exothermic. Positive, you're talking endothermic. When you calculate it, it's delta H of the reaction is equal to the sum of all the delta H of the products minus the sum of all the delta H of the reactants. You do have to multiply that by the number of moles in your chemical equation. So it's kind of heat given off or being absorbed. Here we have H2O solid going to H2O liquid, requires heat. That's heat being absorbed, so it's positive, endothermic. Here we have heat given off by the system to the surroundings. So if heat's given off, it's negative. So that would mean our products are greater than our reactants, and we have something that's exothermic. Okay, so thermochemical equations, negative or positive. If it's absorbing heat, it's positive, it's endothermic. Got it? Okay, here's another one, solid to liquid. If you're going to melt an ice cube, you're going to have to absorb heat, so you can see that it's positive 6.01 kilojoules per mole. And that's per mole, so if you multiplied this whole equation by 2, you would of course have to multiply your delta H by 2 as well. Okay, so here's the second example, the system giving off heat. It would be exothermic, your delta H is negative, and you've got a 890.4 kilojoules per every 1 mole of methane combusted. And so your equation would look like that. Alright, so stoichiometric coefficients are going to be just the coefficients in our equation. We can use those to go and do mole calculations from this. So here, if you reverse a reaction, here we have solid ice melting to liquid water, and it's going to give off heat. Absorb heat, positive. It's going to absorb heat, positive delta H. If we reverse this reaction from liquid to solid, we would reverse the sign of our delta H to make it a negative 6.01. So you can see we move liquid to the reactant, solid to the product. If you flip the reaction, you flip the sign. Very easy to work with. If we multiply each side of the equation by a factor of n, delta H changes by the same factor. So here we took the same equation in the top, multiplied by 2, so we take our delta H, we multiply it by 2, find ourselves at 12 kilojoules. So the physical states of all our reactants and products have to be specified in thermochemical equations. That's important because if you look at Appendix 3 in the back of your book, what you'll see is the delta H for solid water, the delta H for liquid water, the delta H for gaseous water. They're all different. So it's very important. We can't just say, water. We can't just say CO2. I need to know, is it liquid, solid, gas, because those are important. So here they're just showing you how your solid and liquid, we switch those, we get different values. And that's all in Appendix 3. It's very easy to find. So let's see what we have here. 266 grams of white phosphorus burning in air. So if you were going to solve a problem like that, calculate the heat, we're talking about enthalpy, we'll want to write phosphorus plus oxygen for combustion. So P4 plus O2 yields P4O10. Balance that with our 5 in front of the O2. Then we can calculate that delta H by doing our products minus our reactants, and going to Appendix 3 in the back of the book, finding the value for P4O10, finding the values for P4 and O2, multiplying that by 5, and subtracting these, and we'd be in good shape. So if we have 266 grams of P4, we have to get our grams per mole from the periodic table, get moles P4, and then we say if we have negative 3013 kilojoules per mole, then we can get kilojoules per the amount in grams that we started with. So that's how you could solve a problem like that. Always check to make sure your units cancel. You'll be in good shape. So delta H and delta E. Let's see. We're going to compare these two here. We look at the same equation. Solid sodium metal plus water. It's going to be pretty exothermic because the sodium will burn in the water, blow up in the water, something along those lines. Make sodium hydroxide a base plus hydrogen gas. So you have negative, a rather large exothermic reaction. So look at our delta E. So the change in energy. And we look at pressure and our change in volume. Our volume is increasing because we are creating gas and the gas is doing work on the container. So our delta H is negative because we're releasing a lot of heat. And our delta E is negative because we're releasing a lot of energy as well from this reaction. There's a picture of solid sodium, probably with water being dropped on it. And as the water is dropped on it, it reacts rather violently. So specific heat, the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius, and then the heat capacity. This is a little tough from Gen Chem. We just did Q equals Cm delta T, so we use these two pretty much interchangeably, but your text separates them from specific heat and heat capacity. Heat capacity, you'll notice the only difference is a given quantity of a substance by 1 degree Celsius. So heat capacity allows us to take m different masses of these substances into account. And we have these tables in your book, specific heats of common substances that we can refer to do these equations. But basically what you're going to need to know, C is m times S, our mass times our specific heat. And then Q, the heat that's released, is equal to the mass of the substance times the specific heat of the substance times the change in temperature. And then you can kind of take these M and S, substitute those for C, and get another equation for Q. And then of course you know how to find delta T at this point, final minus initial. So you can do a problem like this, how much heat's given off. You have a mass, an iron bar, cools from 94 to 5 degrees Celsius. So you know your grams, you know your delta T. You have to look up S, that would be in your book, your specific heat for iron at 0.44. Temperature final minus temperature initial ended at 5, started at 94, find yourself at a negative 89 degrees Celsius. And then you find your formula for heat given off. M, we've got that. S, we looked that up in the book. Delta T, we calculated that. We find ourselves at let's see. Yep, okay, we know how to do the work. Got it. Units cancel. There we go. Negative 34,000 joules. And so if all your units cancel and you're left with joules, you know you're probably in good shape. Calorimetry, there's a few ways to do it. This first one's called the constant volume calorimeter. And basically they can take this system, this kind of isolated system, measure the temperature, ignite a small bomb within the calorimeter, stir the water around, and ideally all the heat that's evolved from this little bomb will be absorbed by the water. And then this temperature is a direct indicator of how much heat the water is absorbing. And because we know the specific heat of water, then we can figure out how much heat is being released from this reaction. So here we say the heat of the system is equal to the heat of the water plus the heat of the bomb plus the heat of the reaction occurring here. Because there shouldn't be anything else in the system that's really affecting this. We say no heat enters or leaves. So the Q of our system must be 0 if no heat can enter or leave the system. So then we can solve for the heat of the reaction by subtracting the heat of the water, which we have from this guy here, and the heat of the bomb, which we can get from our known values in Appendix 3 for the equations that we use. So Q of water, ms delta T, we know the mass of water, we know the specific heat of water, we know the change in temperature of the water. And then Q of the bomb, specific heat of the bomb, times the change in temperature of the bomb. It does have to stay at constant value, and the delta H does not necessarily equal the heat of the whole reaction. Delta H is per mole. and the heat of the reaction is likely not going to have exactly 1 mole in the reaction. But they should be close. So what do we see here? A constant pressure calorimeter. This is a little closer to something you or I might work with in the lab. Take 2 styrofoam cups, put them on top of one another, put a lid on them, call it good enough. Thermometer goes down through the lid, water's in here, and the reaction occurs in the water. This is something I hope that we'll be doing in a day or two. So the heat of the system is equal to heat of the water plus the heat of the calorimeter plus the heat of the reaction. And unfortunately, this isn't going to be the perfect insulator, but 2 styrofoam cups will do a pretty decent job. So we can say Q of our system is pretty close to 0. Q of the reaction is negative Q of the water plus Q of the calorimeter. We can really solve for it pretty much the same way as we did the other one. So we'll be doing that in just a day or two, hopefully. So here's some heats of typical reactions. Heat of neutralization, acid in a base, yields a salt in the water. Heat of ionization, to break apart into ions. Heat of fusion, go to solid to liquid. Vaporization, liquid to gas. And then a heat of really any reaction, you take all of your products minus all of your reactants, and you'll be in good shape there. Here's kind of a cool biology tie-in to the chemistry world. Is when we say you burn calories, that's actually rather accurate. You consume sugars from your food, and other things too, of course, but a lot of what we eat is carbohydrates, and we break those down into simple sugars. And then using oxygen, we get the energy out of those sugars. And so it is a lot like combustion without the flame. We use enzymes and electron transport and things of that nature to get this sugar plus oxygen to give CO2, which we'll exhale or use in some sort of other metabolic waste, and water, and energy. And there's the energy, negative 2801 kilojoules per mole. So we can kind of compare this. 1 calorie is 4 joules, and 1 calorie that we talk about in the food industry is actually a kilocalorie or 1,000 calories, but we don't write them that way on food labels because it would be depressing to see that this is 120,000 calories in your container of cookies. We say it's 120 kilocalories, drop the kilo, and everybody feels a little bit better about themselves. So here you show some common substances and what you're getting in fuel per gram of substance. Apple, beef, beer, and gasoline. You can see that beef is, of the edible substances on this chart, beef is the highest, which shouldn't be that surprising because protein is going to have your most calories per gram of anything, and so when we consume those calories, it's going to give us heat, negative 8 kilojoules per gram of heat combustion from consuming beef. And then apple has less energy than beef per gram, and then beer has less energy than an apple per gram, and then way at the top, way above beef, is gasoline. Not consumable, but to kind of compare what we're getting from the healthy end of our diet as the beef and apple compared to what our car uses in gasoline, there really is a pretty significant difference when you consider that's per gram, which is an incredibly light amount of mass. So because we can't measure the absolute enthalpy of a substance when we do work with enthalpy, we have to just look at the reactions of interest, which we call these standard enthalpy of formations, and that's our reference point. Basically a fancy way to say Appendix 3 at the end of the chapter. Standard enthalpy of formation is the heat change when 1 mole of a compound is formed from its elements. That's what we use. If it's in its most stable form, that enthalpy is going to be 0 because it's not going to want to release any heat. It's not going to want to bond oxygen gas, not really going to want to bond with a whole lot of things. It's very stable as is, so its heat to give off is going to be 0. Ozone, on the other hand, really isn't that stable, so it has a lot of heat to give off or to absorb to change in a reaction. You have graphite as 0, very stable. Diamond has a little bit to give off, not very much. Diamond's pretty stable stuff, so you can see 142, very high enthalpy, 1.9, pretty small enthalpy. Here's an example of a chart. You've got a much more lengthy chart in Appendix 3, but here's your delta H's for some common substances. And you can see solid calcium's in at 0, solid copper's in at 0, chlorine gas is in at 0, oxygen gas is in at 0 because they're very stable. Very stable things. So let's see, we're working at 1 atmosphere, of course, when you do this. Like I mentioned before, to solve for the delta H of a reaction, you need to take that coefficient into account. So it's products here minus reactants here. And we take that coefficient and we multiply it by the value we find for whatever A is in Appendix 3. So as long as you can effectively work the parentheses on your calculator, you're going to be in good shape there. Hess's law is something we'll interact with just a little bit, but basically it kind of goes back to that state function idea of it doesn't matter how you get to the top of the mountain as long as both hikers make it to the top of the mountain. Hess's law says that when our reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one simple step or in a series of steps. We just have to add the steps. So enthalpy is a state function. Doesn't matter how you get there, only where you start and where you end. So you can kind of think of it like if you were to drive to Sioux Falls, and we'd say, okay, you started in Rapid, you ended at Sioux Falls, and you didn't stop. You drove whatever, 360 miles, 340, whatever it is to Sioux Falls. Now if it occurred in steps, we could say, well, I started in Rapid and I drove to Kadoka, then I stopped, then I drove to Sioux Falls. Well, it's fine. You still made it, 360 miles. You just did it in 2 steps. So if I take Rapid to Kadoka and I add Kadoka to Sioux Falls, I still get Rapid to Sioux Falls. It's the same thing, just some reactions occur in steps. So here's one reaction, graphite going to carbon dioxide. We can add the two, remove those spectators from before. Here you can see carbon monoxide gas and carbon monoxide gas. Remove them both, and you're in good shape. So here you can take, they'll have to give you these little series of half reactions for you to solve this. But if we want to form the CS2, and we're given these reactions, you might have to organize them a little bit. We're going to start with carbon. We're going to start with sulfur. We want to end with CS2. So we don't want that on the reactant side. We want to flip this reaction. And we can do that. We flip this reaction, we change that sign to a positive, and we're going to be in good shape. So that's what we want to get to. Carbon, sulfur, CS2. So we start, and we say we need to start with carbon. So we use this miniature reaction here. And then we get our carbon. Now we need to get 2 sulfurs to make CS2 balanced. So we take our equation for sulfur, we multiply the whole thing by 2. And we take that delta H of the reaction, and multiply that by 2. Then all we need to do is get CS2 to the other side. So we take this equation, we flip it, we take the sign, we change it to positive. Then we just add, straight down here, all the little reactions, and we end up with the value, canceling out those spectators. So we can say for that equation it should be 86.3 kilojoules per mole. Alright, so here we could do the same thing. Benzene burning in air makes carbon dioxide and water. How much heat's released per mole of benzene combusted? If we know that the enthalpy of formation for benzene is 49.04. So we write our equation. Benzene, oxygen, CO2, water. We balance it. We take our products minus our reactants. And we would have to look these values up in Appendix 3. And we would determine that the delta H of our reaction is 5,946 kilojoules. So we did that per 2 moles of benzene. So it would be negative 2,973 kilojoules per mole of benzene. So we found out how much heat's released. Here, kind of a application of this. This is your bombardier beetle. A weird little bug. He's got 2 little chambers in his abdomen that hold separate chemicals. He would not want them to mix in his abdomen, but when they mix outside of his abdomen, it's a neat little defense from other bugs or any other predator. So basically what he's got is this stuff in here called hydroquinone. Kind of gross stuff, but not too bad. Hydrogen peroxide, kind of gross stuff, but not too bad. He keeps hydroquinone in one little pocket. He keeps hydrogen peroxide in one little pocket. And then when something's attacking him, he mixes the 2 into this vestibule and shoots them out of his body. When he shoots them out of his body, the hydroquinone reacts with hydrogen peroxide and forms this benzoquinone stuff. This is a little nastier. I looked it up, and I guess it resembles like chlorine, and maybe hot plastic. And so we look at this reaction, and what we find is that it really releases energy as the reaction occurs. Kind of a lot of energy, like altogether negative 204 kilojoules per mole. That's a lot of energy, and it's enough energy to actually bring this liquid, when they mix, just from the chemical reaction, it brings it to a temperature that's like the boiling point of water. And so the poor thing that's attacking bombardier beetle, another bug, a bird, whatever, is going to get boiling hot benzoquinone sprayed into its, its face, and that would be kind of like boiling hot liquid chlorine being sprayed on you. It's going to make the bug certainly a lot less appetizing, but it is kind of a cool application with biology and chemistry sort of mixed together. Enthalpy of solution is the heat generated when a certain amount of solute dissolves in a solvent. Some solutes will give off heat when they're dissolved. Some solutes are going to absorb heat when they're dissolved. And I don't want to spoil that a whole lot for you, because instead of, working numbers on this, I'd rather have you guys do the lab, find it out, and then build your own hot and cold pack. So we're going to kind of skip this and save the surprise for later, assuming we can figure it out. Here's the solution process for salt ions together. Step 1 is breaking the salt apart. Step 2 is forming salt and water, kind of hydration solution. And so it's kind of a Hess's law thing. If to break them apart takes 788 kilojoules, and to form them together takes 784, then our heat of solution is 4 kilojoules per mole. Kind of a small number. It's why, mixing salt and water doesn't really make it super, super cold by doing that. But you do take step 1 plus step 2 and get your net change for both equations. And that is where we end.